In this presentation, we're going to consider slightly more complicated problems than we had in the previous presentation related to an introduction into mechanical energy. But first of all, let's consider the conservation of energy. So energy can be readily converted from one form to another, and when this occurs, the total amount of energy remains constant. In other words, there is no energy lost. The principle of conservation of energy states the following. Energy is neither created nor destroyed, but merely changed in form. So frequently in mechanics, the potential energy possessed by a body is converted into kinetic energy, and vice versa. So when a mass is falling freely, its potential energy reduces as it loses height, and its kinetic energy increases as its velocity increases. There may be some losses in the conversion, but these can usually be accounted for. So in any system where the conversion of energy takes place, we can apply the following. Initial energy in the system plus energy input to the system equals the final energy in the system plus energy taken out of the system. That can be considered our overarching framework whenever we apply an energy balance or try and solve a problem using the principle of conservation of energy. With dynamics, the initial and final energies in the system are usually the sum of the initial and final potential kinetic energies, respectively. Energy input and output are of the form of work energy, W. Losses due to friction and losses dissipated as heat energy are sometimes denoted by the symbol Q. So the all-encompassing equation we could use states that we have initial potential energy in our system added to initial kinetic energy in our system added to any work in the system, and that can equal the final potential energy of our system added to the final kinetic energy in our system added to any work taken out of the system added to any heat losses. Now for a situation where there is no work done and no losses to occur, the above equation can simplify to initial potential energy added to initial kinetic energy, and that equals to final potential energy added to any final kinetic energy. And we can play tunes on this equation because sometimes we might have initial potential energy but no initial kinetic energy, but we might have final potential energy and final kinetic energy. Or sometimes we might have initial potential and initial kinetic, and that's all going into final kinetic. Or it could be we have initial potential energy and no initial kinetic energy, and then final kinetic energy but no final potential energy. So our equation simplifies to P1 is equal to Ke2. But if we apply the same principle of considering on the left-hand side of the equation initial energies and any work into the system, and on the right-hand side of the equation final energies and any work out of the system, we should be able to determine for our particular question which energies are present on the left-hand and right-hand side of our energy balance. I'll just show you this little illustration here of our roller coaster ride. Imagine that we are on a roller coaster ride, and initially we're at the top of the roller coaster ride, but we're stationary, waiting for the ride to begin. If I was to consider a datum for our particular roller coaster ride at the bottom of the ride, shown here, then in energy terms, we would have initial potential energy, shown here on a diagram, but we'd have no kinetic energy, shown here on a diagram. However, as the roller coaster starts to move from the height of the roller coaster ride down the roller coaster's track, consider say at this position here, there will be a reduction in the potential energy. So the potential energy reduced to this value here. Of course, because we're now moving at some velocity, the kinetic energy will be increasing to some value here. If I now draw a line through this particular position on the roller coaster ride on my energy diagram here, so if I add this small portion of kinetic energy I have here on top of the potential energy I have here, I can see I'll get back to the original potential energy I had in the system. If I now consider the roller coaster ride at its lowest position, this is where the speed will be greatest, and I again draw a line through the energy diagram here. I can now see that the kinetic energy is very large and the potential energy is very small. But once again, if I add this small amount of potential energy onto the large amount of kinetic energy, I end up back with the same energy levels I started with. And that's an illustration of the conservation of energy, in that the total energy in the system remains constant. What we start the roller coaster ride with, we continue that same level of energy along the roller coaster. It's just that it's transferring between potential and kinetic and back from kinetic to potential. Obviously, the roller coaster ride eventually comes to stop because we have frictional effects, aerodynamic drag, frictional effects with the bearings, braking effects, which causes heat and sound energy to occur. So eventually the roller coaster ride does come to a stop, but we can still account for all the energy transfers in the system. The total energy we start with is the total energy we end up with. It's just that it transfers into different forms. Here's our roller coaster ride once more, but this time the datum of the roller coaster ride is taken at the top of the roller coaster, so the datum is actually up here. So if again we initially consider our roller coaster to be at the top of the incline and to be stationary, now the datum is at the top of the incline, then there cannot be any potential energy associated with the roller coaster at that stationary position. So in this particular case, the potential energy and the kinetic energy must be zero, because the roller coaster is sat on the datum we've chosen, so by definition it cannot have any potential energy, and if it's stationary, again by definition it cannot have any kinetic energy. But what happens when the roller coaster starts to move away from the top of the incline, say to position here? Well, obviously as it starts to fall away from the top of the ride, it will increase its speed, so its kinetic energy, shown on this diagram here, will increase. It will become positive because the roller coaster is now moving. However, as the roller coaster now is dropped below the datum, it will actually have negative potential energy, shown here on our potential energy curve. If I again take a slice through my energy diagrams here, I can see that this positive kinetic energy cancels with this negative potential energy, and we end up back with zero energy. We started with zero energy, and as the roller coaster ride starts to progress, we maintain zero energy. If we now consider the roller coaster at the bottom of the ride, where it's got maximum kinetic energy, shown here, it will now have minimum potential energy, shown here, as it's furthest below the datum, so its height is negative in this case from the datum. If we again take a slice through this section, we can clearly see that the maximum kinetic energy, which is positive here, cancels with the negative potential energy. So again, leave us back at the zero energy position. So it would go on for the rest of the ride if no friction effects were present. So I don't know if that helps you, but that's the conservation of energy principle here. Energy is neither created nor destroyed, it's merely changed in form. If we start with a certain amount of energy, potential energy here, then we have to maintain that energy throughout the roller coaster ride in the first slide. And in the second slide, if we start with no energy to begin with, we must maintain no energy as the ride progresses. Exercise 12. A 2,000 kilogram hammer, that's a large lump of metal, is driven downwards under the influence of its own weight and also by an additional steam force of 80 kilonewtons. The hammer falls through a distance of 1500 millimeters before it strikes a forging. We've got to calculate the velocity on striking the forging. Slightly more complicated example than we saw in the previous presentations, slightly more considerations within the energy balance. But I would encourage you to attempt this exercise by first of all extracting all the information from the question, drawing a diagram, and then see if you can generate an energy balance of the hammer above the forging and of the hammer when it's just about to strike the forging. So it's fallen through effectively the 1500 millimeters. The answer is stated here for reference. The full work solution will be shown on the following slide. So here's exercise 12, full solution. So we've got our 2000 kilogram hammer, mass of 2000 kilograms shown here. It's driven downwards under the influence of its own weight and also, notice, by an additional steam force of 80 kilonewtons. So we've got an externally applied force, I've shown it here, F, of 80 times 10 to the 3 newtons. It's also pushing the mass down over the distance of travel here. The hammer falls through a distance or height of 1500 millimeters. Notice I've written that here as h is equal to 1.5 meters. I've also labelled 1.5 meters s as well, as you'll see later on in the solution. I've labelled position 1 here as when the mass is 1.5 meters above the forging, and label 2 here. This is when the mass is just about to strike the forging. So our initial velocity is assumed to be 0, and we're trying to calculate the final velocity. Notice the datum is taken at the lowest point in the system. That's where the hammer is about to strike the forging. So let's now consider the energy balance for this situation. In position 1 up here, we have initial potential energy. If our datum is at the bottom of the travel, then we have potential energy P1 of the mass 1.5 meters above the datum. And we also have work being done because we have a force applied over a distance, or a height in this case, of 1.5 meters. So we definitely have work being done on the hammer on the mass of 2000 kilograms as it moves from position 1 to position 2. On the right hand side of the equation, the only energy we have out of the system is kinetic energy, because we've got some movement now of the mass. As it's fallen through the 1.5 meters, it's now gained kinetic energy of motion. So we have kinetic energy, no potential energy, because at position 2 we're now on the datum that we chose, and there is no work out of the system here because the question does not refer to any frictional losses or resistance to motion. So we assume no friction effects to consider, and therefore no work out of the system. So there's our energy balance. Initial potential energy plus work into the system is equal to final kinetic energy. The potential energy and the work all transfers to kinetic energy. And that will allow us now to find the velocity on impact. So if we now insert the equations for the various forms of energy, potential energy is mgh, work done is F times S, and the output kinetic energy is a half mv squared, or mv squared divided by 2. Notice it's the v we're trying to find in this question. So transposing the equation to find v, we multiply both sides by 2. Notice the use of the bracket here. We must have a bracket around the mgh plus F times S, because both terms are multiplied by the 2, and we divide throughout by the m. That's equal to v squared. To determine the final solution, we just square root both sides. So there's our final solution for v. V is equal to the square root of 2 multiplied by, in brackets, mgh plus fs, all divided by m. Inserting the numerical values, in this case, the m is 2000 kilograms. We know g is 9.81 meters per second squared. The h, the height fallen, is 1.5. We add to that the steam force on the hammer is 80,000 newtons, and we multiply that by the distance the force acts, which again is the 1.5 meters. That's all divided by the m, which is 2,000. Evaluating, we find the velocity on impact of the hammer with the forging is 12.2 meters per second. I would encourage you to verify that calculation for yourself. Exercise 13, quite a complicated problem here. This time we have a car of mass 750 kilograms and it's pushed up a slope of 2-degree incline by applying a constant force of 400 newtons. And that's applied over a distance of 35 meters. We're informed there is a continual frictional force of 25 newtons against the motion. We've got to calculate the speed of the car after being pushed up the incline, assuming it commences from rest at the bottom of the incline. The answer is shown here. I would encourage you to start the presentation and try and attempt that question. It's quite a difficult question, lots of information there. As always, I would suggest draw a diagram first of all of the car at the bottom of an incline and then the car at the top of the incline. Extract the information, label the diagram appropriately, and then try and apply your energy balance of initial energy and any work into the system is equal to the final energy and any work out of the system. The full solution is shown on the following slide. So here's the solution to exercise 13. So we have a car of mass 750 kilograms, shown here. It's pushed up a 2-degree incline, it's shown here. We're applying a constant force of 400 newtons, so F, applied over the distance of 35 meters, so F is 400 newtons. The distance travelled is 35 meters, shown here. And we're informed that there's a continual frictional resistance of 25 newtons against the motion. So I've shown that force FF here for frictional force of 25 newtons. We've got to calculate the speed of the car after being pushed up the incline. So that's this speed here we're trying to find, assuming it commences from rest. So initial velocity is 0. So as we can see from the information given, we need to find the vertical height h that the car moves through as it progresses up the incline of 35 meters at 2 degrees at the horizontal. Notice I've stated that the datum is at the bottom of the incline, the lowest point in our system as usual. So the first thing we need to do is to try and calculate the vertical height h, I suggest. I'm sure some of you can see straight away the function we need. It's a sine function, but if you're unsure, you can write down your soccer toe mnemonic and you can determine from that which function it is by ticking off information that you know and then deciding what you're trying to find, and that should highlight which function. But it is a sine function in this case, you'll see. So sine of 2 degrees is equal to the opposite side, that's h in our triangle, divided by the hypotenuse, that's 35 meters. So just simply transpose the equation to find h. So multiply both sides by 35. So h evaluates to 1.221 meters in this case. Let's now consider the energy balance. Our initial energy plus any work into the system is equal to the final energy plus any work out of the system. So considering the energy at position 1 here, we have no kinetic energy because the vehicle is not moving. We have no potential energy because the vehicle is on the datum. But we do have some work into the system because we have 400 newtons applied over a distance of 35 meters. So we definitely have W1, we have work into the system. If we now consider position 2, when the vehicle is at the top of the incline, at height h above the datum, we can now clearly see we have potential energy as the vehicle now has some height above the datum. We have kinetic energy because the vehicle is moving, we're trying to find the velocity. And we have some work out of the system because we're told there's a frictional force of 25 newtons that's constantly resisting the motion over that 35 meters. So we definitely have work out the system. So from our energy balance this time, on the left-hand side of the equation, we have work into the system, and on the right-hand side, that work is transferred into potential energy, kinetic energy, and also we lose some work out the system due to the frictional effects. So here's now the full work solution to exercise 13, trying to find this velocity at position 2 at the top of the incline. So inserting the equations for work, potential energy, kinetic energy, I now get F multiplied by S on the left-hand side of the equation is equal to mgh, potential energy, plus half m v squared, plus the friction force times the distance travelled on the right-hand side here. We're trying to find V, so transposition-wise, I'm first of all going to subtract the mgh and the ff multiplied by S from both sides of the equation to get the mv squared upon 2 on its own on the right hand side, and then I will multiply both sides by 2. Again, notice the brackets being used around the terms on the left hand side because each of those terms is multiplied by 2, and I will divide throughout by m. So square rooting both sides, my final solution is V is equal to square root of 2 multiplied by, in brackets, the Fs minus the mgh minus the friction force times S, all divided by m. Inserting the values, the force constantly applied up the incline on the car is 400 newtons. The distance travelled is 35 meters. We subtract from that the mgh, where the mass of the vehicle is 750 kilograms. We know g, as always, 9.81 meters per second squared. And the height we calculate is 1.221 meters. We subtract from that the frictional force, 25 newtons assumed constant, over the 35 meters travelled, all divided by the mass of 750 kilograms. So the velocity at the top of the incline, V, evaluates to 3.32 meters per second. Again, I would encourage you to check that calculation for yourself. Here's the full solution for exercise 13. I'll leave you with some tutorial questions related to potential and kinetic energy. Questions 1e, 2e and 3e shown on this slide do not really require an energy balance. They're essentially questions based on the previous presentation where we introduced the energy concept, so slightly simpler questions. But question 4e does require an energy balance because we're considering a roller coaster there that starts at some height and the roller coaster drops through some distance, so an energy balance can be considered there for potential to kinetic transfer. Notice the mass is not stated in question 4e because if you put the correct energy balance down, the mass will actually cancel out from the calculation. The answers to each of the questions are shown in the brackets. And question 5e through to question 7e, again, I would encourage you to use the energy balance concept to analyse these problems. Again, the answers are shown in brackets. Here's some more tutorial questions. Tutorial questions continued. And the final tutorial questions. Answers, as always, are stated in the brackets. Here's the bibliography used to help generate the presentation. I hope this has been of interest to you. Thank you for viewing.